So we're going to start our unit on thermodynamics. And thermodynamics, in this unit, it's going to be coming from two chapters out of your book. In this unit, we're going to be studying about spontaneity of a reaction, whether it's spontaneous or non-spontaneous. We're going to learn about the concept of entropy, which is the measure of disorder in the system. And we're going to learn about the free energy of the reaction, known as Gibbs free energy. First definition I want to cover with you is the definition of energy. Energy is defined as the capacity to do work or to produce heat. We have potential energy, which is the energy due to position or energy due to its composition. The energy of an object at rest is another way that you hear potential energy defined. And we have kinetic energy. Kinetic energy is the energy due to the motion of the object. So the energy of an object in motion is kinetic energy. Now, in the chapter that we studied on gases, we learned about how to calculate the root mean square velocity of the gas. And that had to do with the kinetic energy of the gas particles. Remember, gas particles are in constant random motion. But another formula we can use to calculate kinetic energy is equal to 1/2 the object's mass times its velocity squared. So 1/2 mv squared is a formula that we could use to calculate kinetic energy. A fourth definition is the law of conservation of energy. This is actually the first law of thermodynamics. The law of conservation of energy states that energy can neither be created nor destroyed in a chemical or a physical reaction, but it can be converted between forms, from one form to the other. As I just mentioned, the first law of thermodynamics is also known as the law of conservation of energy. Basically, what the first law of thermodynamics states is that the total energy content of the universe is constant. The total energy content of the universe is constant. So in science, we have to define our system and the surroundings. The system is what it is we're studying. Let me bring my pen up. So when you're talking about the system is whatever it is you're studying, whether it's a cube of ice, a reaction taking place in a beaker, and then you have the surroundings around it. Now the system plus the surroundings is what we define as the universe. So what the first law of thermodynamics means is that the total energy of the universe is constant. If the system has heat leaving it, we call that exothermic, then the surroundings is gaining energy. And if the system absorbs energy, we call that an endothermic process, the heat going into the system, then the surroundings is where the heat is coming from as it gets absorbed into the system. So it's an exchange of thermal energy between the system and the surroundings. So in a reaction, you cannot create nor destroy energy. You can transfer it from one form to another, and it can be transformed or transferred from one place to another. But the pathway has to be defined. Is it absorbing the energy, or is the system releasing the energy? The energy of the universe is constant, though. So let's talk about a state function. We have state functions and we have path functions. Well, state functions are functions that depend only on the present state of the system. Energy happens to be a state function. So let me talk about that a little bit more. So I know it might be hard to see, but there's a person standing on top of Mount Everest here. So we have a person standing here on top of Mount Everest. And so the person standing up here on top of Mount Everest has the same potential energy, whether they got up there by hiking all the way up from the bottom, or if someone were to have flown them over in an airplane and they parachuted and fell down from the plane. So the point is that the potential energy of the person is relative to its position. It doesn't matter how you get there. The point is that you're there. Energy is a state function. It doesn't matter how you got to that amount of energy, how you got to that point. There may be 10 different ways to get there, but what's important is that you are there. It's independent of the pathway taken, in other words. Now, work, something else we're going to talk about here, is not a state function. Work is considered a path function. So let's look at why that is. Delta E is the formula we're going to look at here that stands for the energy change in a system. So delta E, we can write a formula to calculate that where it's equal to Q, which is the heat, thermal energy, plus the W, work. W is the symbol for work. So the overall change in energy is equal to Q plus work, or heat plus work. So delta E represents here the change in the internal energy of a system. So Q represents the heat flowing into or out of the system. Q is going to be negative if the energy is leaving the surroundings, because you have to base it on your reference point. If energy leaves the surroundings, the heat is leaving. So we call that exothermic. So we say the heat is negative because it's exiting the system. Q will be positive if the heat is entering the system from the surroundings. So that's an endothermic process that we talk about. So the sign of Q is based on the direction or the path that it took. W stands for work. The work can be done by the system or on the system. Work is going to be negative if work is done by the system on the surroundings. Again, very similar to like if the system is losing energy, we say the heat's negative. It's the direction, it's exiting. Well, if the system does work on the surroundings, it's negative is the sign we give to the work. Work's going to be positive if the work is done on the system by the surroundings. So if the surroundings do work on the system, then we give the work a positive sign. It's all based as a reference point. So here we have two examples, endothermic and exothermic. So here we have the system, and the system is what's going to be represented by this oval here, and then around the system is the surroundings, and then consider the whole box representing the universe. Reactions in which energy flows into the system as the reaction proceeds is called an endothermic process. So here, what sign will we give the heat? That's right, we would give it a positive sign, positive Q. The surroundings are losing heat, but the system is absorbing heat. So we always reference the heat of the system. The heat of the system is positive. The heat lost by the surroundings will be equal to the heat gained by the system. So this is an endothermic process. Exothermic reactions are reactions in which the energy flows out of the system. So here's your heat, the Q, flowing out of the system. So in this case, the Q of the system, the heat of the system, is negative because the energy is flowing out, and the Q of the surroundings is positive because the surroundings gained the heat.